Hey everyone, this is Dr. Walker. In this video, I'd like to go over the second example from v575, finding the force between wires. In this example, we have three wires. We have two long wires that have a current I2 here in the same direction, and they're a certain distance A apart. And then we have another wire with a current I1 here, which is above the first two, and it's being levitated, and we want to figure out what current does it have to have so that it's levitated such that it makes the three wires form an equilateral triangle. So the first thing to figure out is, why is this wire being levitated? Well, we learned that when two wires carry currents in the opposite direction, they're going to repel. So wire 1 here is going to be repelled upward by both of the bottom two wires. Let's draw a free body diagram from this front view here. If we draw an equilateral triangle, which is what we want, we have the two currents here going into the page, the two I2s here, and then the I1 coming out of the page. So it's going to experience a magnetic force due to each one going upward. And this wire here has a finite length, and it has weight, where we're given the mass of it. And so we know that it's going to have a weight going downward. If the three wires are to form an equilateral triangle, then these angles here will be the same, and the x component of both of these magnetic forces, we can call them FB, they both have the same magnitude. The x components are going to cancel each other out. So what's going to happen is that the y component of each force, FBY, both of these two components are going to cancel out the weight pulling that wire down. So this is an equilibrium problem. In the y direction, we're going to say the sum of the forces, and we're just looking at the magnitudes here. The sum of the forces in the y is equal to 0, and we're going to have the y component, and we need to define an angle here. Let's go ahead and define the angle with respect to the vertical. Let's define angle theta here, so it's going to be the same one as this angle theta here. Alright, so the y component is going to be adjacent to that angle, since that angle is the same as this one, so it's going to use cosine. So each FBY is going to be FB cosine theta. So we're going to have FB cosine theta plus FB cosine theta minus FG here going down. The sum of all of these y forces is going to be 0. And what is FB? Well, first of all, we can just write this as 2FB cosine theta minus FG. FG is just a weight mg. And now we just need an expression for FB here. Well, we learned in this video that the magnetic force per length is equal to mu naught times I1 times I2 over 2 pi A, where A is the distance between the two wires. So FB, we're just going to multiply both sides by L here. That's going to be the FA. The distance between the two wires is in fact A, because we want an equilateral triangle. So we're going to have 2 times mu naught I1 I2 times the length over 2 pi A minus mg equals 0, so let's just set it equal to mg. The 2's will cancel out, and we're trying to solve for what current must the long wires carry. We have the current of the finite wire, so we're looking for I2 here. We're going to go ahead and solve for I2. That's going to give us mg times pi A divided by mu naught I1 and L. And I dropped my cosine term here. Let me put that back in there. I forgot this cosine term right here. All right. So now we just have to plug in all of these numbers. The mass is 400 grams. Convert it to kilograms. It's 0.4 kilograms. G is 9.8. Then just put in pi. A is 1 centimeter. Convert that to meters. 0.01 meters. And then plug in mu naught, which is 4 pi times 10 to the negative 7. So the pi's do cancel out. It's a nice thing about the permeability constant here. The current is 100 amps for I1. The length is 10 meters. And cosine, we do need to figure out what is this angle theta here. Well, we have an equilateral triangle, so it is half of the angle, which is 60, so it's going to be 30. And we can plug in all of these numbers. We're going to get 113 amps for the current in each of the long wires in order to levitate the finite wire so that it makes an equilateral triangle, so that all three wires make that equilateral triangle.